So looking at page 64, improper integration, these are instances in which you have one bound of your integral that is either asymptotic or approaching infinity in some capacity. And so we need to account for that because you can still capture an area in some cases, even though it may not seem that like that's necessarily something that's possible. So what we do is we actually use limits because what we, in the process of finding a limit, we have techniques that allow us to approach infinity. So while we can't actually get to infinity, we can see what's happening, what the behavior of a function is as we get closer and closer to infinity. All right, so what we do is we swap out an infinity for some dummy variable and apply a limit as that dummy variable approaches infinity. All right, so I have a solved example here for you, the 1 over x squared one, so I'll let you read that one on your own, but let me take you through a couple exemplar problems. So in the case of number 1, you have 1 at the integral over the interval of 1 to infinity of 1 over x dx. All right, so if you have a sense of what 1 over x looks like, then that's wonderful. If not, then I would say type it in and get it and get a sense. All right, so zoom 6. All right, so you're looking at, it's a rational function. So you can see here that we're only concerned with the part that's in the first quadrant. All right, because that's going from 1 to infinity. So what you can do is you can adjust your window to go from 1 to something large. 10 would be all right. We don't need any negatives. So what I'll do is I'll go from negative 0.1 just so I can see the y-axis. I'm sorry, the x-axis. And y max, I definitely don't need to go that high, so maybe like 3. And so that's what we're looking at. All right, so that's the graph, and what we want to know is how much area will be captured if we were to go from 1 out to infinity. All right, so the way we handle this, we handle it by not handling it. No, so that infinity, we're going to let a be infinity. All right, and so what we'll say is the limit as a approaches infinity of the integral over the interval of 1 to a of 1 over x dx. All right. The antiderivative of 1 over x is the natural log of x, going from 1 to a. All right, so that's going to evaluate to the natural log of a minus the natural log of 1. 1, the absolute value of 1 is 1, so natural log of 1 is going to go to 0. So we're looking at ln of a. All right, now we need to apply the limit as a approaches infinity for that expression. All right, and so we would be asking ourselves, all right, so where's this going, And so the way we handle this is by first taking care to establish that that a value is not really necessarily required to be in an absolute anymore. All right, and the thought process there is that, well, if we're going towards a positive infinity, and the interval that we're working with starts off with a positive 1, kind of makes sense that we probably don't need the absolutes because everything's going to be positive anyway. So I can rewrite this as the limit as a approaches infinity of the natural log of just the plain old a. Now I can evaluate my limit by substituting an infinity in, and I'd be looking at ln of infinity. The natural log of infinity is infinity, and so we get no solution here, but instead of saying no solution, we would say this diverges. It doesn't converge on a particular area because it's always going to be accumulating more and more area. All right, so this diverges. All right. Now the second one is going from negative infinity to 0. Now we can swap the bounds of integration and negate things and transform if we want, but we could also just let infinity be a, right? So let a be infinity and have it go from negative a to 0. All right, so I'd be looking at the limit as a approaches infinity, going from negative a to 0, and then we'd have this 1 over the square root of 4 minus x dx. All right, so take a look at that picture. So we're only concerned with negatives here. So alpha y equals n over d, 1 over the square root of 4 minus x squared. I'll just do a zoom 6. Let's see, we got a little bit of a negative piece here. So I'm only concerned with, I mean, really think about the domain. It's only going to go out as far in terms of x. Let's see, on the positive side, it's only going to go out as far as 4. But then on the negative side, it should go out. Oh, why did I put a power of 2 in there? Jeez Louise. I was like, why does this seem to not make sense? All right, how about we try that again using a technique I like to call the right way. All right, so we got a whole lot of graph on the left side, but it does max out at 4, right, in terms of x. But we don't even care about that because we only want it to go as far as 0. All right, so let's say negative 10 to 0. Doesn't go very high at all, so let's say negative 0.1 to 2 or 3. And so that's what we're looking at, and it's just a question of, and again, it does seem to be asymptotic, it's a question of whether it'll converge and give us a true area. All right, so we start the process of integrating. This can be rewritten, and we could use U substitution, we can rewrite then use U substitution, and it's really up to the user defined. All right, so du, I'm going to use U substitution in case you hadn't noticed yet. Right, so this is going to be negative dx. All right, my bounds. Now I can actually manipulate my bounds to be consistent with my u. All right, so u of 0 is going to be 4. U of negative a is going to be 4 minus negative a, so 4 plus a. All right, so I'm looking at 4 plus a of 4, 1 over the square root of u. Now I need to swap out the dx, so I'm going to negate both sides, so negative du is equal to dx. So this is going to become negative, and I'll slap on a du here. So then u, negative u to the negative 1/2 du over the stated interval. Or, that is my lasso tool. All right, so 4 plus a to 4. We'll worry about the limit after the fact. Increase the exponent by 1, you get u to the 1/2. Divide by the new exponent, dividing by a half is the same as multiplying by 2, so negative 2. And then we'd be looking at 4 plus a going to 4. All right, so negative 2 times 4 plus a to the 1/2 power minus negative 2 times 4 to the 1/2. We could simplify. All right, 4 to the 1/2 is 2, times the negative 2 that's already there is negative 4. Negated is positive 4. So we're looking at negative 2 times 4 plus a to the 1/2. That's what our antiderivative would be, but now I need to find the limit as a approaches infinity. All right, so this expression gives us all of this stuff. Now I just want to see where this is going to take us. Now, a radical function does increase. It increases slowly, but it increases. All right, so one way to handle this would be to say, okay, well, I'm going to substitute an infinity in there and just go by my general understanding of functions. Another way to do it would be to type in this expression, -2 times, I'll use x's instead of a's, sorry. Raise it to I'll write 0.5 just for convenience, plus 4, and then go into my graph or my table and see what's going on here in terms of as I'm increasing my x values. All right, it does seem to be increasing the y values. Is it a question of without bound, or we'll go from there. Second window, table starts 0, change in table, make it like something like 100, and you see that even if you continue on the process, and bearing in mind that it's not increasing at a very rapid rate, but it is still increasing, it never levels off. So this one also diverges. All right. So are they all going to diverge? Well, that's a wonderful question. Well, the answer is no, because we wouldn't have the need to say diverge if there wasn't a converge. So we're getting there. One bridge at a time, though. All right. So the next one looks very much like maybe a partial fraction situation, because the bottom is factorable. All right. So the numerator is just a 1. I mean, there's a dx there, but it's really just a 1. If we're going to break this down using partial fraction decomposition, I'm just going to pull out the 1 over dx plus 2x plus 3. That's going to be a sub 1 over x plus 2 plus a sub 2 over x plus 3. And then we'll multiply through. So we'll get 1 equals a sub 1 times x plus 3 plus a sub 2 times x plus 2. Distributive property, 1 is equal to a sub 1x plus 3a sub 1 plus a sub 2x plus 2a sub 2. Alright, so I have no term on the left side that involves an x. So a sub 1 plus a sub 2 is going to be equal to 0, which means 3a sub 1 plus 2a sub 2 is going to be equal to the 1. Alright, a and a sub 2, a sub 1 and a sub 2 are opposite, so I'll say a sub 1 is equal to negative a sub 2, which allows a substitution here. 3 times negative a sub 2 plus 2a sub 2 is equal to 1. Negative 3a sub 2 plus 2a sub 2 is equal to 1. That's going to give me a negative a sub 2 is equal to 1, which means a sub 2 is equal to negative 1, which means a sub 1 is equal to a positive 1 because they're opposites. All right, so I now know that I'm looking at the antiderivative of 1 over x plus 2 plus negative 1 over x plus 3 dx. So ln x plus 2 minus ln x plus 3. All right, that's all to address the antiderivative part of it. All right, so I got a little ahead of myself here because we also need to account for the fact that this is an improper integral. So we're looking at the limit as a approaches infinity, going from -1 to a of dx over all this good stuff, x squared plus 5x plus 6. So I now need to evaluate this from -1 to a, and then once I do that, I'll find the limit as a approaches infinity. So I'm going to plug in the a. So natural log of a plus 2 minus natural log of a plus 3 minus ln -1 plus 2 is going to be a 1 minus ln negative 1 plus 3 is going to be a 2. Natural log of 1 goes to 0. We can make some fractions out of this, kind of clean it up a little bit. So I can make this part ln of a plus 2 over a plus 3 minus a negative, so plus ln of 2. All right. So now I'm going to apply the limit as a approaches infinity. Of all of this. The second part is the nice part, because the limit of a constant is a constant. The first part's a little weird, so I'm going to rewrite them separately. And I'm just going to leave this off as just a natural log of 2, because like I said, the limit of a constant is the constant. So it's really just this piece that I got to worry about. All right. So one technique that we can use allows us to pull the natural log out of the limit. This is a kind of an obscure Calc 1 topic. The limit, I'm sorry, not limit, natural log of the absolute value of the limit as a approaches infinity of a plus 2 over a plus 3. All right, so the limit of a function is the same as the function of a limit. So it's the limit of the natural log function of its composite function is a plus 2 over a plus 3. So what I'm doing is I'm doing that in reverse. I'm finding the limit of the inner function and then applying that to the function that it's composed into. All right. The exponents are the same here. So this is the limit as a approaches infinity of ratio of the coefficients is 1. Limit of a constant is a constant. So this is the same as saying 1. Natural log of 1 is equal to 0. So the final answer here is actually just the natural log of 2. So this one actually converges to a final answer. And what this is telling us is that if we were to graph this equation, y equals 1 over x squared plus 5x plus 6 going from -1, hit the wrong thing, I want to hit window, -1 to something big, so I'll just say 10. Oh, let me make that a -10. I saw a negative and I saw a 1 and didn't register. All right, so we have some graph, I would imagine, living in this neighborhood. All right, so let's take a look at our points. Oh, let's make that, so second window for table setup, let's make that 0 and 1 again as a default. Go back into the table and see that we're looking at values that seem to be decreasing. All right, but they already start off very small. So at the x value of -1, the biggest value it'll ever be is 1/2. So let me make my y max something like 1/2. All right, so now I'm very long on the low side here, so let's make that, I'll make that 0. All right, so this is what we're looking at. It looks like something very much like an exponential, well, it's exponential in nature, but it looks like a geometric relationship. We'll get to that more in the next unit. But what we're looking for is the area that's captured on this interval. And what this is telling us is that even though we could never get to infinity, if we could, the amount of area that would be captured would be equivalent to the natural log of 2. So a way of verifying, it's not really verifying, it's more like just kind of convincing yourself that you didn't just do all this for nothing. If you do Second trace, option 7, take your lower limit of -1 and an upper limit, I put 10 here. It'll give you the 0.613. So what I would do is I would just type in the natural log of 2. 2 is positive, so I don't need the absolutes there. 693. They said 613. All right, so if I went further, maybe I would get that, you know. And so -1, let's say I want to go to 50. Oh, invalid because I didn't give myself the domain. Quit. I got to make my x max 50. So we graph it. Second trace 7, -1. Type in the 50 and see what that gives me. It gives me 0.764. Again, we're saying 0.693. It's getting closer and closer. So if you increase that upper bound, make it something like 500, 1,000, 10,000, whatever, odds are you're going to get closer and closer, and at least convince yourself that that natural log of 2 is reasonable.